Structural isomers. Organic compounds exhibit a phenomenon called isomerism. Isomerism occurs when two molecules have the same chemical formula but different molecular arrangements. That causes them to have different chemical properties. There are two major types of isomerism. Structural, which has three little sub-bullets here: chain, positional, and functional. And then stereoisomerism, otherwise known as spatial, a little easier to pronounce. And you have geometrical, conformational, and optical. And here's an organization chart of isomers. We have structural, divided into chain, positional, and functional. And then spatial, geometrical, conformational, and optical. Chain isomers have different arrangements of their atoms. This is an example of a straight chain versus a branched chain alkane isomer. Sharing the same chemical formula, which is C4H10, the difference in structures will result in differences of chemical and physical properties. Positional isomers have the same atoms and molecular formula, but have atoms or groups located in different positions. Below is an example of a pair of alkene positional isomers. The double carbon bond is in different locations. Some more positional isomers. The below alkanols have the OH group, the hydroxyl group, on different carbon atoms. And then the methyl group here is also on different carbon atoms. This is on what? The second from the left. This is the third from the left. Functional isomers have the same chemical formula, but different functional groups. Since functional groups determine the behavior of a molecule, these isomers can function very differently despite having the same formula. So here is C4H8 as an alkene, and here it is as a cyclic alkane. The alkene on the left, with the double bond right over here, is highly reactive, and the cyclic alkane is not very reactive. Acetone, otherwise known as propanone, and propanol have the same chemical formula, but different functional groups and different properties. Down here, we have ethanol and diethyl ether also have the same chemical formula, but because of their different functional groups have different properties. So ethanol is an alkanol, right? And it has an OH over here connected to an alkyl group. The ether has this single oxygen here bonded to a carbon on either side, making it an ether. And they have very different properties. Some more chemical formulas. All right, here's the acid and an alkanote. Same chemical formula, but acetic acid. And here's the functional group that makes it an acid. And then methyl ethanoate. Here's the functional group that makes it an alkanote. And then below we have an alkyne and an alkene. Same chemical formula, different structure, different properties. One of the things you'll be asked to do with isomers is to draw pictures of them. So here, let's draw a straight chain and branched isomers for C6H14. Start by drawing the straight chain isomer. So we have 6 carbons, so we connect them all up like this, and then we put the H's around them, so each carbon has 4 bonds, and you'll find, hopefully, that that's 14 H's. There's only one way to draw the straight chain, but there are often multiple ways to draw the branched chain isomer. For the branched isomer, let's choose some of the N carbons, which have been circled in red here, and we'll move them. We'll attach them to one of the carbons, this carbon here, the third from the left, which is over here, and here are the 2 carbons and their hydrogen atoms. We move them along. Make sure you check that the number of carbon and hydrogen atoms are correct according to both the molecular formula and that every carbon has 4 bonds. Example 2. Draw 2 structural isomers of C3H6. Start by drawing the straight chain isomer, but be careful. Draw this double bond here between 2 of the carbons so you only use up 1, 2, 3, 4, 5, 6 hydrogen atoms. Next, arrange the carbons in a cyclic pattern and add hydrogen so that all carbons have 4 bonds. Then check if the number of carbon and hydrogen atoms are correct according to the molecular formula. Well, we have 3 carbons and 1, 2, 3, 4, 5, 6 hydrogens. We're good. Example 3. Draw 2 positional isomers of C5H11OH. Start by drawing all the carbons in a straight chain without adding any of the hydrogens. Do this twice. So we have 2 chains of 5 carbons each. Choose a non-terminal carbon, so don't choose this guy or this guy, and attach the OH. Be sure to choose a different carbon on each molecule. So this is on the second one here after we crossed out the terminal one, and this is on the third, so we're good. Add the hydrogen so that all the carbons have 4 bonds. And finally, check if the number of carbon and hydrogen atoms are correct according to the molecular formula. Well, each one has an OH, so that's going to be over here. So we need to have, what, 11 hydrogens. We've got the 5 carbons. That's pretty straightforward. Then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yep. And then the bottom one is also correct.